the instructions for the ray tracing software here. Please take a look at it. After Tim will go over it, but make sure you do take action before the class on September 24th, which is next Tuesday. I also posted 2 interesting articles here. Very interesting approach to solar desalination. Definitely everyone's encouraged to read it, but definitely the teams working on solar desalination, please click on it and read through it. There's some very interesting, it's very short, obviously, so you can read through it. It gives you, potentially give you some interesting ideas. We talked about this article here as well. Assignment 2 instructions are here. I'll briefly mention it at the end of the class as well. Okay. So today we are going to finish the rest of non-imaging optics. So last week we talked about non-imaging optics. So we're gonna complete that today, and which is here. And on Thursday, we'll talk about radiometry, photometry. Next week, we have ray tracing software tutorial and the midterm review. So make sure you attend those 2 lectures for sure. And then the following week is assignment 2 being due. Okay, October 3rd. So keep in mind the schedule. Okay, so let's actually begin here. Just to review what we talked about last week. We talked about what's called a compound parabolic concentrator, which the idea was to design a 2 parts of a parabola. Maybe this picture is better. Let me, oops. Hold on. Okay. Put that up there. And okay, so we had what's called the CPC. That is the entrance aperture of the CPC. That is the exit aperture of the CPC, and it is comprised of 2 parabola. One parabola is shown here. Okay, and we ignored the dashed lines. We only use this part of the parabola, and the second parabola is shown here, which is a mirror symmetry. And the mirror symmetry is across this axis, the vertical axis here. So the rays come in. So for instance, this ray comes in, it reflects off this point and reaches this point. That's the edge ray. And the opposite happens for this ray, and so on and so forth. And the idea is that any ray that comes in between this acceptance angle marked here will end up at this location, somewhere here, okay? And then we also found out that the concentration factor of a CPC, which is the ratio of the area of the input divided by the area of the output, is inversely related to the sine of this angle. In other words, if you want large concentration, you can only accept a small range of angles. If you need to accept a large range of angles, you need to give up on concentration. Now, by the way, when you talk about accepting small range or large range, that is very critical to designing a tracking system. So if you need to only accept a very small range of angles, that means you need to track the sun very, very precisely. So that's it's an important engineering condition that we should keep in mind. Whoops. And then we want to go through this stuff fast. We talked about the acceptance angle, just remind ourselves. And today, okay, we talked about that. Today, I want to focus on the properties of the CPC, particularly related to 2D and 3D. So we'll start with 2D. And the conceptual understanding is simple, but let's try to look at it visually. So first, we're going to so before I go into the goal, here's the following. The CPC maximizes concentration. So in other words, this is the best you can do. And we are simply trying to show this in a slightly different manner. And the reason to do this is not to prove a theorem or something, but just to gain intuition into what the CPC does and to get some practice in applying thermodynamics in these sorts of concentration systems. So bear with me as we go through this. First, let's look at a cylindrical black body at some temperature T. Okay, cylindrical meaning this is an infinitely long cylinder, okay, which has a radius r. And of course, it's infinitely long, but we're going to look at some unit length 1, Lu equals 1, okay? And we're going to call the source SR. And this source, you can think about it as a sun, for instance, but of course it's cylindrical, so that's artificial. And it's sitting in space at 0 Kelvin. And then we're going to look at another cylindrical surface at a distance d away, okay? So it's a big cylindrical surface with the radius equal to d. And we're going to place a one-dimensional CPC here, as shown here. So it's basically a linear concentrator, or a one-dimensional concentrator. And of course, these are drawn in 3D, and you can take a slice and look at it in 2D as well, which we will do in shortly. But let's first go through the thermodynamics very briefly. So first, the total flux emitted by a black body of area dA, some small area, and temperature T into a hemisphere is given by the hemisphere is sigma T before dA. So this is the Stefan-Boltzmann law, right? Stefan-Boltzmann constant times temperature raised to 4 times the area. So this gives the total flux. Now, our black body has length, let's say Lu, which is a cylindrical black body. Its surface area now becomes the surface area of the cylinder, which is 2 pi r times Lu. So 2 pi r times Lu becomes this dA. So now you have 2 pi r Lu sigma T raised to 4. Now we're going to make Lu equals 1 because we're going to look at unit length. So the flux emitted per unit length is simply 2 pi r sigma T raised to 4. Okay, so far so good. So again, this is the flux emitted by the cylindrical black body per unit length. It's 2 pi times radius times sigma times T raised to 4. Okay, so far so good. It's emitting everywhere into space. Now we're going to look at a top view, which is a cross section. So you can see that is our source now. Think about it as the sun at some temperature T, radius is r, and some distance d away, way out here, we have the Earth, let's say, and we have a CPC here. It's a linear concentrator. It's a two-dimensional CPC. And we're also going to say the input aperture is A1 and the output aperture is A2. We're going to put up a solar cell or a black body at A2. Okay. So if we now look at this entrance aperture, we want to calculate how much flux is intercepted by this entrance aperture. So in this previous equation, we computed how much flux is coming from the black body, from this source. Okay, that was 2 pi r sigma T raised to 4 per unit length. Here we are trying to calculate how much is actually accepted at this input aperture. So the amount of radiation or flux the entrance aperture A1 receives per unit length, therefore, is simply the area of this entrance aperture divided by the whole area, which is this big circle, times whatever is coming from here. So sigma T raised to 4, 2 pi r over 2 pi d times A1. So this d is, of course, the big cylinder here, over which the flux is spread out over, and we are just intercepting this small portion of it. So A1 over 2 pi d is the fraction that we are collecting with the CPC. Okay, so pretty simple. So just that fraction. Now, of course, the 2 pi's cancel out, and you get a simpler expression. Now, we're going to assume that there is a black body that absorbs the radiation at the exit aperture A2. As I said before, we're going to put a solar cell here. Okay, solar cell or anything that absorbs light, we're going to treat it as a black body. Now, when you first put this black body here, it's going to be at some temperature, room temperature, whatever. But eventually, it will reach the same temperature as the source, assuming there's nothing else in the universe, right? We're considering a very simplistic system where this black body essentially thermalizes, reaches the thermal equilibrium with the source, which means that eventually this black body will reach the same temperature as the source. Okay, so originally the temperature of this black body used to be less than T. At equilibrium, it will be T. Then this black body will also emit radiation. Okay, and now, by now, we're very familiar with how to calculate this. Black body will also emit radiation with flux per unit length given by sigma T raised to 4 times its area, which is A2. Okay. And I'm saying area here because it's unit length, right? Because into the screen of this paper, we are going to assume unit length. So it's A2 is really just the side here. A2 times 1 is the area. Now, that's phi2. That's the radiation which is emitted by the source, by this black body. And phi is the radiation which is entering the CPC. Now, these two things have to be equal at equilibrium. Otherwise, the temperature is changing. Right? When we say equilibrium, the temperature is stabilized. So they have to be equal. So whatever coming in here must be equal to whatever is leaving. So phi should be equal to phi2 under thermal equilibrium. So we put these two together and get a very simple expression. A1 R over D is A2, or A2 is A1 sine theta, or the concentration, which is A1 divided by A2. Remember, A1 divided by A2 is a concentration, is 1 over sine theta. Now, sine theta is just R over D, right? Because you can see this triangle here. That's the tangent, so that's 90 degrees. That's R, that's D. So sine theta is R over D. Okay, so we essentially regenerated the equation that we learned in the last lecture, but now using basic thermodynamics. Okay, previously we just used geometry. So you can see kind of a connection between completely different modes of physics to some extent, and they are related, obviously. Another way to draw a conclusion from this this equation is that here we did not make any assumptions about what the geometry of the CPC is. We did not say it was a parabola, right? But we ended up with the same equation. So another way to say this same thing is that now we can conclude that the best you can do from thermodynamics is this, and which is the same as what a CPC does, which means that the CPC is the best you can do based on thermodynamics. Okay, so it's kind of a logical argument. Apratham, did you say something?
No.
Okay. Now, if we look at this a little more closely, again, this rest of the space is 0 Kelvin. So the radiation leaving A1, going out of this CPC and coming from A2 can only be headed to the source here. This implies that the acceptance angle of the CPC with the entrance aperture A1 cannot be larger than theta. Okay, because theta is the largest angle of light coming from the source to the CPC. Now, as d, the distance goes to infinity for constant theta, this radius goes to infinity, so it just becomes a very big source. A1 becomes a straight line, and the concentration factor becomes A1 over A2, 1 over sin theta. You don't have to worry too much about it. It's just saying that if this distance is very large, instead of having a curve here, we will have a straight line. Okay, and then it becomes exactly like the CPC that we have been talking about last week. Again, this is the maximum possible concentration for 2 dimensions. This is the same as the CPC, so the CPC gives the maximum possible concentration in 2D. Okay, so this is an important equation, and you should have some intuitive understanding of what that means. Okay, of course, the next thing remaining to understand about the CPC is 3 dimensions. So what happens when we extend this analysis to 3D, concentration in 3D? So of course, now our source becomes a sphere, like the sun. Okay, the temperature T, has radius R. And our CPC now becomes like a 3-dimensional object, and we're going to look at a big sphere over which the light is spread. And we're going to intercept only that portion of that sphere, flux. Okay. So this concentrator, let's imagine it's on Earth. And you can also look at the vertical cut through it, and it looks exactly the same as before. You have this big circle, so it's a cut through the sphere. And that's our CPC. Again, just be aware, the area, input area is A1, output area is A2. Okay, so the flux emitted by the spherical source SR is just the same as before, sigma T raised to 4 times the surface area. So the surface area of the sphere is 4 pi r squared. 4 pi r squared times sigma T raised to 4. The radiation captured by the entrance aperture A1 for A1 is 4 pi r squared sigma T raised to 4, which is total spread over this big giant sphere, okay, divided by the area of that big giant sphere, 4 pi d squared, multiplied by the area of the CPC, input area. So that's the fraction that's collected. Okay? This is the fraction of this divided by the whole huge sphere. Of course, the 4 pi's cancel out, so you get a simpler expression here. That light which enters the CPC then gets concentrated onto a black body at the exit aperture A2. And at thermal equilibrium, this black body heats up to some temperature, same temperature T, and the radiation that A2 emits must equal that it receives. So that's the thermal equilibrium. In other words, what is coming in here must equal what's leaving from here. So again, we will make this equal to this. So 4 pi r squared sigma T raised to 4 divided by 4 pi d squared times A1, which is the amount of flux that is entering the CPC, should be equal to the flux that is leaving the black body, A2 sigma T raised to 4. Cancel out all the things that can cancel out, like sigma, 4 pi, and all that, and you get a very simple expression. A1 over A2 is d over r squared. Now d over r is 1 over sine theta, or r over d is sine theta. So A1 over A2 is 1 over sine squared theta. So the concentration factor, which is A1 over A2, is 1 over sine squared theta. As d goes to infinity, r goes to infinity at a constant theta, and A1 tends to be a flat surface instead of a sphere. So that's just a detail that we don't need to worry about too much. So the key is in 3 dimensions, concentration factor goes to 1 over sine squared theta, whereas in 2 dimensions, it goes as 1 over sine theta. Of course, this also means that the problem of acceptance angle trade-off versus concentration factor is more severe when we talk about the 3D, right? Because of the square factor. Remember, sine theta is less than 1. So when you square it, it gets even smaller, right? Okay, and you'll see this in some of the examples, problems. Okay, now let's think about one more design concept, okay, for the CPC. So far, let me go back here. When we thought about the CPC, we thought about the CPC being completely hollow, right? Light is, this is air inside or vacuum inside, light's bouncing around and reflecting and reaching the output. But it can also be solid. If you recall in one of the videos that we saw last week, this does not have to be hollow, it can be solid. And if it's solid, you have the advantage that it becomes total internal reflection, okay, which is really nice because the reflection is 100%, right? There's no loss in the ideal case. So it also has one other advantage, is that its refractive index, when you have a solid material here, is larger than that of vacuum. So the refractive index here can be larger than 1, and that actually helps you. This has some deep physics, but really all we need to understand is that it helps us because the Stefan-Boltzmann constant is proportional to n squared, n being the refractive index of the medium. Okay, all this stuff is constants that we saw before. You can ignore that. Key is that sigma is n squared times sigma in vacuum. So simply by filling my CPC with some material, I can increase sigma. And if I can increase sigma, if we go back to this equation, you will see that that's a big advantage. So remember, the source is still in vacuum. So in other words, if I look at this picture, the source is still in vacuum, but I'm putting this in some material whose refractive index is n. So I'm going to write this equation once more, okay, where this sigma is the sigma in vacuum, and this sigma is now n squared times the sigma in vacuum. So you see, this is the same as before, but now here I've added an n squared because of this equation, right? Because I've filled my CPC with some material of some refractive index n. Now I get a new equation where the ratio of the area of the input divided by the output, which is concentration A1 over A2, n squared over sine squared theta. Okay, so in other words, I have increased my concentration factor by a factor of n squared without doing anything other than just filling my CPC with some material. That's great, right? Because I don't have to do anything, just fill it with water, for instance, right? I can increase my concentration without giving up on the acceptance angle. So that's a really nice design possibility as well. And this is, of course, in 3D. In 2D, this general result becomes A1 over A2 is n over sine theta. So should be aware of this possibility. Now, let's also look at this from something we saw for geometrical optics, Snell's law. Okay, this can also be understood from Snell's law. So if the CPC is made of a material of index n, okay, so we have the CPCs here. This is vacuum or air, and this is n. You have a ray of light that comes in at some angle to the normal of theta. Of course, it will bend at a slightly different angle following Snell's law at, let's say, an angle theta prime. Okay, this is a half angle here. And we know that theta prime is less than theta, and they're related by Snell's law. Sine theta is n sine theta prime, right? So we can simply write A1 sine theta prime is A2, right? We know that from, we have derived it before from geometry, if you recall. Last week we derived A1 being the input aperture, A2 being the output aperture, A1 sine theta prime is A2. And simply substitute sine theta prime to sine theta divided by n, we get A1 over A2 is n over sine theta. So simply from Snell's law, we can derive this equation as well. And this is all related because really, from a thermodynamic point of view, what n really provides is what's called degrees of freedom or degrees of density of states in optics. Something you don't need to understand, in any detail, but just be aware that this n, the presence of some material which slows down light, allows you to essentially cram more density of electromagnetic energy into space, and that's what allows you to do this extra concentration. Okay. So let's look at a practical example where something like this has actually been used to produce irradiance on Earth that exceeds that on the sun's surface. Okay, this is a typo. This should be sun surface, not Earth surface. So this is a paper from 1989 by a fairly famous guy, a person called Roland Winston, who's considered the father of non-imaging optics. Its title is Concentration of Sunlight to Solar Surface Levels Using Non-Imaging Optics in Nature. So first, let's take a quick look at what is it trying to do, okay? So let's just read it very briefly. The flux at the surface of the sun is about 6.3 kilowatt per centimeter squared. So this is centimeter squared, not meter squared. So the units are a little bit different than what we're used to. It falls off at the square of the distance to a value of about 137 milliwatts per centimeter squared above the Earth's atmosphere, or typically 80 to 100 milliwatt per centimeter squared the ground. Okay, so we know this from our second week lectures. In principle, the second law of thermodynamics permits an optical device to concentrate the solar flux to obtain temperatures at the Earth's surface not exceeding the sun's surface temperature. In practice, conventional means for flux concentration fall short of this maximum because imaging optical designs are inefficient at delivering maximum concentration. So in this paper, non-imaging light gathering devices can improve on focusing design by a factor of 4 or more and approach the thermodynamic level. So they're saying we have used a non-imaging design to concentrate terrestrial sunlight by a factor of 56,000. So that's their concentration factor, producing an irradiance that could exceed that of the solar surface. This opens up a variety of new applications to make use of solar energy. Okay, so let's kind of take a look at what they did because it's interesting. So it's a fairly simple setup. First of all, they have a mirror.
Dr. Menon, I think your video is lagging behind. Like, did you change the slide? It just shows the writing slide right now.
Okay, I just changed the slide, yeah.
Yeah, it's... yeah, now it changed. So it's lagging behind quite a lot.
Okay, I'll try to slow down. Okay. So here, they have a concave mirror here. So it's a silver mirror. The sun is here, sunlight comes in. It bounces off this 40 centimeter silver mirror and focuses onto the silver cone. So this cone is like a CPC, but it's a slightly modified version of the CPC. They call it, it squeezes the light from 1 centimeter to 1 millimeter. So it takes the input light here, 1 centimeter to 1 millimeter. So there's two stages of concentration. One is concentration from the 40 centimeters to 1 centimeter, right? 40x times squared. And that's going from 1 centimeter to 1 millimeter. That's a million. So, no, sorry, 100 times, right? 1 centimeter, 1 mm is 10x times squared is 100. So the total effect here is that light is about 60,000 times brighter than normal sunlight. And this is just some detail of that. It's kind of like a CPC, but it's solid in this case. And they're taking advantage of the refractive index of the solid material, as you will see in the next slide. So here you can see a simplified version. So the light's coming in. Obviously, only direct sunlight is captured, so they have to track the sun very carefully. Light's then focused in to this non-imaging secondary concentrator that we saw before. And the light is then focused into what they call a calorimeter, which is then used to measure how much the temperature is increased. And you can see the details of this part here, where the light's coming in. The image of the sun is here. There's a lens here which collects the light onto this oil-filled calorimeter, which is a calibration heater. So it has a very precise way to measure temperature using thermocouples. Not so important for us. That's the idea. And this whole thing is oil-filled silver vessel. So because of the oil, you get the higher refractive index, which allows you to essentially increase the concentration factor. So I forgot to point out one quick thing. So here, if we do the calculation, it goes from 40 centimeters to 1 centimeter. That's a 40x, okay? But 40x in one dimension, so 40 times 40 roughly is 1600, right? 1600. And then 1 centimeter to 1 mm is 100. So 1600 times 100 is 160,000. But of course, there's some efficiency losses here, which ends up with about 60,000. And they take advantage of the higher refractive index as well. Okay, so this is kind of towards the end of the class, but let me, because today's lecture will be short, I'm going to skip that. Yeah, actually, let's go through this again very quickly. I'm not going to go through it, but let me first ask if there are any questions about what you need to do for assignment 2. It's due on October 3rd. I gave you pretty clear instructions here. Okay, guess no questions, so let's keep going. Feel free to email me if there are questions. So the last part of the class I want to spend, and Apratham is going to lead on a brainstorming session, okay? And I'm going to show you 2 example projects, okay? One related to, they're both related to solar tracking. And then I'm going to ask you to do a brainstorming project on solar tracking and one on designing a non-imaging concentrator. And Apratham will lead you on this discussion. So first, let's look at a very, very simple example of a solar tracker. And this is really very simple. It's actually from, I think, like a middle school science project or something. So let's take a quick look at this. And when you look at this, I want you to think about doing a brainstorming session. How will you improve on this? Okay, so two brainstorming sessions. The first one is how will you improve on this? So let's take a look at this first. And I will walk you through it. I'm going to, so the goal is to track the sun, okay? And I like this project because, of course, it's a young kid who's doing it, and it's a very simple idea. So hopefully it'll inspire you to think about interesting solutions, but simple solutions. Now, So I'm going to pause and ask, can you hear the video sound?
No.
Okay, then I will narrate. So you can see, turn that down. So you can see there's a solar panel, okay? And the idea is she's using the solar panel to drive a motor, which will point, it will always point towards the sun, essentially. And you can see the basic idea is that if it's pointing slightly away from the sun, there is a mismatch in the output from these two solar panels, and that will drive the direction of the motor that turns the turntable. In other words, yeah, so you can see in this example, she's pointing the light on one side, it'll turn. Towards the light. And she's just saying that the motor is simply from a CD player, so quite cheap, simple. And the direction of the motor, and there's many more details, but I'll kind of stop there. Okay, so again, I'm not going to show you the full video because it's long, but what I want you to think about is this very, very simple idea, right? Here, basically using two panels facing the sun, and as one shades the other, it just changes the differential output from the solar panels, which then drives a motor to bring it back. And it's kind of analogous to some extent to how like a sunflower tracks the sun. I want to show you one, and you're going to do a brainstorming session on how to improve on tracking the sun, because that is applicable to all your projects, I believe, or many of your projects. Let's look at one more video. This is actually from ARPA-E, which is an energy-related innovation agency of the federal government. This is from a few years ago, but you will see one more example. Actually, I'm going to see if I can play this. It's going to.
The concentrated types of solar, you basically have a robot.
Can you hear this?
These solar panels or these mirrors at the sun.
Can you hear the dialogue?
Yeah.
Okay.
Yeah.
Let's just play this. It's very short.
So very high accuracy. And when you do that with metal and motors, at some point it ends up that the solar, it's not really a good trade-off to do solar anymore, because you're using so many resources and you're doing it so expensively. It's not really accessible to most of the world. So we're working on a new form of solar tracker that's based on plastic and water actuators, as opposed to the traditional metal and motor-based actuators. This is the actuator we're basing our solar trackers on. We call them heliostats because they follow the sun. Over here we have a very small scale version of our array, and our actual array would maybe have 100 mirrors this size. And these mirrors are much smaller than what's out in the field right now, and there's a lot of advantages to that. One of them is the closer you get to the ground, the less wind loading is a problem. And because it's so lightweight, we could start thinking about putting concentrated power on rooftops, places where we haven't been able to do it before because it's such a heavy system. One of the mirrors on this array is demonstrating movement, and the movement is happening just by distributing water to each of the chambers. Instead of having a motor on each of these, instead you'll have a centralized control system that just routes the fluid where you want it. So you have one small control system that can control up to 100 or more of these in the field, which makes the cost of control very low. There's very few people doing robotics that is fluid-based, and definitely no one in the solar industry is doing hydraulics in this way. Well, if everything's successful, we're introducing something that could make solar energy at coal parity cost. So solar power could actually be as cheap as any other form of energy, which would be very enabling.
Okay, I'll stop here, and now I am going to to continue the brainstorming session. So the question I want you, and I'm going to give you one more question before I sign off, actually. So the first brainstorming question is, how would you improve on the solar tracker? So you saw two simple examples. One was very simple, which is the traditional approach of a motor, but some clever optics combined with, electronics, let's call it. And the second was some sort of fluidic hydraulic approach. So the first brainstorming question, and I want you to you can pair into groups, your project groups if you want, just your neighbors, either way, but discuss among yourself. How would you build a more effective? It could be cost effective, maybe more energy effective. It could be lighter. Some advantages. How would you build a tracker? Okay. And the second question, which I will leave with Aperture, is I want you to do a practice of design a concentrator that will concentrate sunlight into a ring. And Aperture is very familiar with it, so he'll lead you on this. And I'm going to one last thing just to point out, there is a very interesting TED Talk that I would encourage all of you to take a look at. The website's it's linked on a course website. At this point, I will stop